welcome back. Today we are going to be talking about PCA, aka principal. This tablet is quite not calibrated. Principal component analysis. Okay, so what's the idea here? With principal component analysis, this is a dimensionality reduction technique. Okay, what does that mean? It means we reduce the dimensionality of our data. And you may say, how can you do that? If you have a 100-dimensional signal, you can think about it as a vector with 100 components in it, right? How could I reduce this to 30 without losing any data? And the answer is you can't, right? You fundamentally can't. You will lose some data. There will be some error in your signal. But here's the idea. Okay, so instead of thinking about a 100-dimensional signal, let's think about a 2D signal. So let's think about some data that we have that may be two-dimensional, maybe a correlation between a person's age and their height. Okay? Actually, let's do it better. Let's do one that might be even more correlated. Let's do person's height, okay, and their weight. Okay? So, if we were to plot that data, right, and we'd put height here and weight here, we would maybe get, okay, this person has this height and this weight. Someone with more height is going to have more weight, maybe a little bit lower here. We'd get data that maybe looks like this. How about that, right? Roughly as someone's height increases, so does their weight. That would make sense, right? Now the question is, this is 2D data. This data is two-dimensional, right? We need two axes to represent it. If I wanted to represent this data only using one number line, only using one axis, which direction would be the best way for me to smush my data? As in, let's say I choose to only represent it using this axis. Then I'm going to project all of my data points onto that axis. So let me see if I can make it clean up. This is my axis, right? Then I'm going to project all my data points. This point is going to come down here. This point is going to come down here. This one here. This one, right, is going to come directly down. So let's do that and see that, look, oh, we're getting a lot of overlap. We're getting a lot of overlap. And so the key idea to realize is we want to maintain as much spread as possible. We want to maintain as much spread of the data as possible, right? The fact that these 2 points, when we project downwards, they're going to be overlapping. So there's not going to be a difference shown in the 2 points, when in reality there is a difference, right? They're different weights, right? Even though they may be the same height. So by similar logic, I'm going to have to take this out because I'm a little bit dumb and I forgot that I have to undo, but whatever, okay. If we were to project onto the weight axis, again, we have some overlap. So I'm sure a lot of you are seeing that the best axis to choose looks to be this axis, right? Because we project here, okay, no overlap, here no overlap. Yeah, a little bit of overlap here, it is what it is. But here no overlap, here no overlap, right? We're maintaining as much of the variance, the spread of our data as we can, okay? So we are maintaining the variance of our data, okay? That's the idea. So if what PCA would do is it would take this two-dimensional data and project every data point onto this axis, which we call the principal component. Okay? So a key idea to have in your head is the principal component. You usually have multiple. So the principal components are the components of max all the way up to min variability. Okay, so here, because our data is two-dimensional, we have two principal components. The first one is this one, and the second one is this one. Principal components are always perpendicular to each other. We will see why. By the way, this will be a little bit of a longer video, but it should give a good full overview into, let me make sure I'm recording, into PCA. So anyways, what was I saying? Principal components are always perpendicular. So this one is the first direction of max variability, and this is the direction of minimum variability, right? You see if we collapse it along this line, wow, we're getting tons of overlap. No good, right? If we collapse this onto here and this onto here, very bad. Okay, so let's figure out how we actually deal with the math, okay? There's one thing, when you look at this data here, there's one sort of idea I want to get at, which is the idea of covariance. Okay, so let me maybe switch to a blue color. Okay, so covariance. Okay, we all know regular variance, okay, from stats is defined as the expected value of x minus the expected value squared. So it's on that. Remember, in general, you can think of expected values as just being means. They are means, they're average. So it's saying on average, how far is each point from the average, right? So if I have, this is my average mu here, right? And let's say my points are here, 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 right? It takes this distance, squares it, takes this distance, squares it, takes this distance, squares it, and then takes the average of those distances. That's it, right? It's an average distance of distances, okay? Now covariance is a little bit trickier because it actually measures, so this variance is all measured in x, right? The covariance measures in a variance between two different variables. So the covariance between two variables x and y is given as 1 over n minus 1. This is just the number of data points minus 1. It's a normalizing, averaging factor, right? Times the sum of xi minus x bar. Let's not use x bar, let's use average. Okay, average of x times yi minus average of y. So what are we doing? We're going over all points I. So let's say I is 1. That's our first data point, x1, y1. We're subtracting away the averages from x. So pretty much we're centering this data. So if this is our data here, and we're looking to calculate the covariance, the first thing we're going to do is center this data. So take this data and move it to the center. So instead of moving the data, what I'm going to do is actually a little bit smarter. I'm going to move the axes. So I'm going to take my little... Again, as I've said before multiple times, I need better software eventually. Make sure you like and subscribe and share these videos so maybe I can get a sponsor or something, or YouTube can give me a bit of revenue. That'll be nice. Alrighty, let's move these axes. So now that we've subtracted off that mean, our data is somewhat centered. Then we're pretty much, now that the mean is 0, right, we've subtracted off the mean, right, we're centered the data. This term is now 0, this term is now 0. And now we're basically just doing xi times yi. So again, this shows this should be a positive covariance, right? Why? Because as x goes up, y also tends to go up. It's kind of like a measure of slope in 2 dimensions, if you like to think about it, right? So if the covariance of x and y is high, that means, right, as x increases, so does y. Okay, so here, this formula should be very intuitive, right? We would want a high covariance here, and we do get it, right? Because here we have a point like positive x, positive y. Those are going to multiply, right, and be positive. Then negative x, negative y. Those are also going to be multiply and be positive. Negative x, negative y. So together, we're going to get a very high covariance when we do this sum out. And that's good, because that's the relationship we have here, right? Okay, that's the idea of covariance. It's going to be very important in PCA. Anything else? No, I think we're ready to get started. So what I'm going to do is I'm going to take you through how PCA works, but with a very cool example, which is we're going to be using the example of face recognition. So we're going to learn how PCA works for face recognition. Okay, so I'm going to, let's see, I think I can take this out. Okay, let's now start, and I'm even going to take this out. Okay, so how are we going to perform face recognition with this random PCA thing, whatever I've been talking about? All right, let's see. So face recognition. Okay, the first thing we get is a data set. We get a data set of faces. Now you're like, okay, faces, how do they even connect to numbers? Remember, an image of a face, right? An image of a face can be split up into a bunch of tiny, tiny pixels, way tinier than I'm drawing here, right? And those pixels each just have values, which represent how bright that pixel is, right? So really, an image, a face, can be represented as a matrix of numbers. Usually, for now, let's say our matrix is 64 pixels by 64 pixels. Okay, that's our matrix. So this is one face. One face, right? Let's say it's a face of some smiley guy. Okay, that's not. I was gonna draw his whole body, but okay, here's our happy guy. Okay, it takes up 64 by 64. Okay, let's take one of these images and flatten it into a long vector. Remember, we're basically gonna take, if this row reads 1, 2, 3, 4, all the way to 64, then this row reads 65 all the way to whatever, 128. We're gonna go 1, 2, 3, 4, 64, 65, 128, all the way down. So we're basically gonna take these numbers and flatten them into one vector. What's the dimension of that vector gonna be? 64 squared, which is 4096, which I looked up beforehand. I didn't do that in my head. Okay, so now we have a 4096 by one vector, and this is pretty much one face. Okay, but we can't do any sort of PCA on just one face. Let's say we need a data set, right? Let's say we have 100 faces. So if we have 100 faces, okay, what we're gonna do is take those 100, each one of those, and now we're gonna stack them as columns of a matrix. So we're gonna have a matrix that's 4096 by 100. Okay, does that make sense? Each column here, this is gonna be my first face, whatever, all the way up to 4096. And there's gonna be a different face. There's gonna be a third and a fourth, and I'm just gonna have this 100 different faces here. So if I were to reach in and pull out any of these columns and expand it out, that would be a 4096 by 1 vector, which is again, just if you were to re-put it back into a face, it would make a face. It would be a 64 by 64 grid of pixels that will make a face. Make sense? Okay, very nice. So we know what our original matrix looks like. This is the data matrix that we'll get. Okay? Now, what do we do with this data matrix? Well, let's think. Let me make some space here. Apologies for the delay. Maybe think about what I've been saying in the meanwhile. Maybe think about why PCA is so cool. Isn't it very cool how we can actually reduce the dimensionality of our data and still make it make sense? So we'll see what we mean by that. And you're gonna learn by the end of this video how face recognition works, which is very nice. It's a pretty cool technology. Okay, so let's take this matrix we have. I want to use purple. Let's take this matrix that we have. Okay, actually I'll go back to black. I think I need to be a little bit more normal. Okay, the police is outside, or police car is outside. All right, so 4096 by 100. Okay, remember, we're going to find the covariance of this matrix, of this data. Okay, now this is crazy because before we were talking about covariance with two variables. Now we have like 100 different variables, right? We have instead of having 2 columns, we have 100 columns, right? So this is a little bit different, right? We're going to do the same process though. We're going to subtract off the mean first. So step 1, okay? So step 1 is what we call standardize. Standardize. So we find the mean, find average of each column, okay? And then subtract. We subtract it away. What I mean is, let's say this first column was 1, 2, 3. Let's say this first column was all ones to make it easy. For whatever reason, you have a face that's not even a face, it's just a bunch of ones, whatever. Right? We take the average of that column, so the average of all ones is going to be 1, and then we subtract that. So we subtract that average from each one of these points. So this whole column would turn into 0, 0, 0. Make sense? Okay? Then, okay, let's call, so now we have new matrix. Let's call that X. Okay? Then step 2 is to find covariance matrix. Okay, so now this is interesting, I didn't mention this, but now we're looking for not just covariance, but a covariance matrix. So what that looks like, okay, is it's gonna have all, it's gonna look, so what's the best way to, let's do it for 2 dimensions, what the covariance matrix would look like, okay? It would have covariance of x and x, covariance of x and y, covariance of sorry, not x and y there, y and y, covariance of x and y, and covariance of y and x. Okay, so basically what the covariance matrix is, I'll call it, it's usually denoted with a sigma. Okay, so not a C. I don't know why I wrote a C. That was kind of dumb, right? But in each element, it has a specific covariance. Okay, so as you can imagine, this extends from multi-dimensional data. When you have more than, when you have 100 dimensions, we're gonna have a 100-dimensional covariance matrix, right? But either way, let me go back to my pen. Right, this sigma matrix, covariance matrix, in the top left corner has the covariance of x and x, which, by the way, is the exact definition of the variance of x. There's the variance of x. Down here it has the variance of y. And you can see that, right? If I just replace, if I find the covariance of x and x, then I'm replacing x, then I'm replacing y with an x here. And you can see in mu x, that's just xi minus mu x squared, which is xi minus the expected value squared. And we take the expected value of that, the average of that. So that's just the variance in the first place. Okay? So make sure you see that connection. And here we have the covariance of x and y, and here we have the covariance of y and x. Okay? Technically, I could use sigma squared for variance, whatever. I don't care. Okay? So to find the covariance matrix, which is this thing, we have our matrix X that we've centered and standardized. We do 1 over n minus 1, so number of samples, so 100, times x transpose times x, or x transpose, either way, whichever one is gonna. So let's say x transpose x, and we'll see why. Okay, so because the important thing is, because so let's first of all see why this works. Okay, so why does this formula give out the same covariance as before? Well, look, I'll do it right up here. Oh. Hey, get thicker. Okay. Why? Well, look, imagine I had a simpler 2D data set. Okay? Imagine I had a simpler 2D data set. So imagine my data set was x1, x2, x3, y1, y2, y3. Okay, so see how each of these are like pixels again, but just I'm just doing a simple image. This could be a 2 3x1 images or whatever. Okay, first we subtract the mean, right? So we're taking the mean across the column, so we're finding the mean in the x direction, and we're finding the mean in the y direction, and we're subtracting that away. So we're turning this matrix into x1 minus mu x, right? x2 minus mu x, x3 minus mu x, and then y1 minus mu y, y2 minus mu y, and y3 minus mu y. And if I take this matrix, and you can do the multiplication for yourself, this is now my matrix X, right, as we showed here. If you take this and multiply by its transpose, or the other way around, you're going to get out, so this is once again, this is a 3x2 matrix. So if I do the transpose of this times by itself, I'm going to get out a 2x2 matrix. And in each of the, let's do the matrix. Let's do the multiplication out. Why not? So x transpose is going to be, okay, so let's write it out. This is x. X transpose is going to be, take all the rows and write them as columns. So x1 minus mu x, y1 minus mu y, x2 minus mu x, x3 minus mu x, y2 minus mu y, y3 minus mu y, and now multiply it by our original matrix, which was x1 minus mu x, y1 minus mu y. Okay, and I'll just leave the first row for now, or I'll write this x2 minus mu x, x3 minus mu x. Okay, I'll write the whole thing. Hopefully this is helping you see it. I apologize for the terrible handwriting. I'm very smushed, but okay, let's multiply this out. So this row times this row, right? In this entry, I'm going to get x1 minus mu x times x1 minus mu x. So that's x1 minus mu x squared, plus that squared, plus that squared, right? So I'm going to pretty much get the variance of x, right? For this one, I'm going to do x1 minus mu x times y1 minus mu y. That's the first term. x plus x2 minus mu x. You see how this is genuinely just going to give me the covariance of x and y? Here I'm going to get the covariance of y and x, and here I'm going to get the variance of just y. Okay, so that's why this gives us out the covariance matrix. Okay, next, third step. Let's clear some of the board. And I have an example of PCA, but I think we're going to do that in the next video just because this will get a little bit long otherwise. Okay, so technically you need 2 videos to fully understand PCA because I think the example is very, very, very important. The numerical example, just see how it's done by hand one time. Okay, all right. So once we've done that, we're going to find the eigenvectors. Becomes skinnier. Step 3 is find eigenvectors, eigenvalues, and eigenvectors of the covariance matrix. Okay, why do we do this? Why do we do this? The covariance matrix represents the variance. It represents the variance across your image of different variables with different variables, correct? Now, we want to find the eigenvectors and eigenvalues of it because that will tell us the directions of maximal variance, right? And that's what we care about when we're looking to do something like facial recognition. I want to know where do the vectors, where do the values in my image differ the most? Because for someone, if I'm looking to compare 2 faces, right, everyone has a nose, right? Everyone has eyes. I don't care. Knowing that something has eyes is not going to help me recognize. But if I know someone has a beard versus someone doesn't, and I'm able to recognize that beard pattern as being a variant pattern and something that changes, that's going to help me recognize the face a lot, right? So, a few things. The covariance matrix is symmetric because these guys and these guys are always going to be the same, because if you take xy in this formula and flip it around yx, it's the same thing. Multiplication is commutative, correct? So because the covariance matrix is symmetric, there's a theorem that says eigenvectors, okay, of a symmetric matrix are orthogonal. In other words, perpendicular. Very important. Let's prove it real quick. Let's say our matrix, covariance matrix is sigma, okay? So we have 2 eigenvectors and 2 eigenvalues. Let's say we have sigma v equals lambda v, right? So v is our first eigenvector, and lambda is the eigenvalue associated with that. And then we have sigma mu equals sigma u equals mu u. A little confusing with the notation. Actually, let's just use alpha u. Okay, so lambda is the eigenvalue associated with v, the eigenvector, and alpha is the eigenvalue associated with u, the eigenvector. Okay, we're going to use the fact that, think about what this, now I'm going to write something here. I'm going to say that, okay, what does, let me do this in red, or in a different color, I'll do it in brown so it's different. Okay, what does u transpose times sigma v look like? As in, sigma v is just lambda times a vector. So this thing is a vector, right? Again, v is a vector, sigma is a matrix, so a matrix times a vector is going to give you a vector. And then a vector multiplied by u, which is also a vector transposed, this is going to be a simple dot product between these two. So we're going to get out a number. So if I take the transpose of this, correct, that's the exact same. So basically what I want to say is that this thing right here, because it's a scalar, it's exactly equal to its transpose. All right, do we all agree? That's true, because this is just a number, and a number is always equal to a number transposed. Now, let's apply the transpose property. We know that when we transpose, we can flip the order, right? So we know that A, B, C transpose is equal to C transpose, B transpose, A transpose. That's a fundamental property of transposes. That's important to know. Okay, so let's apply that here. That this is going to equal to V transpose, sigma transpose, U transpose. Correct? But what does sigma transpose equal to? Because sigma is symmetric, the definition of symmetric means that its transpose equals to itself. So this equals to V transpose sigma U transpose. Okay? Now, not U transpose. Sorry, it should not be U transpose. It should be U. It should just be U. Because U transpose becomes U. Sorry, there should be U here. Okay? Now we go in here and we replace everywhere that we see. So here we see, let's do yellow. Sigma v is going to become lambda v because we know sigma v equals lambda v from the eigenvalue. So u transpose times lambda v equals, and here sigma u is going to become alpha u. So v transpose alpha u. Okay, for these two things to be equal, right? We know alpha cannot equal alpha cannot equal alpha cannot equal lambda because they're different eigenvalues, right? That's eigenvectors of symmetric matrix. What I mean is eigenvectors with different eigenvalues. Okay, so this implies that whatever's remaining has to equal 0, right? That this v transpose u has to equal u transpose v, which is equal to 0. Okay, and that means that they're orthogonal. Okay, so we've proven that u and v are orthogonal. Okay, nice. So let's go back here. We find the eigenvectors and eigenvalues of the covariance matrix. Okay, once we have them, once we have these eigenvalues and eigenvectors, we put them into our own matrix. So actually what we do is let's write it like this. Get out. Okay. Next what we're going to do, put eigenvectors into matrix, sort from increasing to decreasing eigenvalue. What I mean is that if we end up with these eigenvalue of 3, the eigenvector is 1, 1, 1. Eigenvalue of 2, the eigenvector is 2, 1, 2. And eigenvector of 1, the eigenvalue is 1, 1. Eigenvalue of 1, the eigenvector is 1, 1, 1. We're going to put them in a matrix in this order. 1, 1, 1, 2, 1, 2, 1, 1, 1. Okay? This, let's call it, what do we want to call it? A. Okay? The transpose of this is your PCA transform. Okay, so let's take a second of what we've done. Okay? What we've done is we've found the covariance matrix, we've found its eigenvectors, and we've put them in columns. Now, when I do A transpose, right, my covariance matrix becomes the rows. The rows are the eigenvectors, right? And then what I do, this PCA transform, okay, this PCA transform, what allows me to do is it's going to be projecting. So let me give an example. So let's say this is my data here, just for simplicity, okay? We have an example. Always think about things with numerical examples. Okay, so let's say A, my PCA matrix is 1, 1, 1, 2, 1, 2, 1, 1, 1. Then A transpose, my PCA transform is going to be 1, 1, 1, 2, 1, 2, 1, 1, 1. Okay? A transpose times any vector V, what does it do? It takes in a vector V. Okay, so this could be an existing face, okay? And projects onto the principal components. Which remember, the principal components are these eigenvectors. Okay, so let's say I put a vector in 1, 3, 4. When I do this matrix multiplication, my first row times my first column is the projection, right? It's a dot product. It's going to be the projection of this new face or old face onto the principal components. So what I do, okay, so how this would work with facial recognition. Let's say 1, 3, 4 represents Bob's face. Okay, so over here, let me running out of space. Okay, I'm going to take this part out. Sorry. Give me a moment. Okay, I'm going to take this out. Okay, here's like the big idea. What we've learned is the components of maximal variance. So we want to project, okay, we want to project all of our data onto those components so that we can really understand what's going on here, right? It gives us the best understanding of what's going on. Okay, so again, here's my A transpose matrix, right? 1, 1, 1, 2, 1, 2, 1, 1, 1. Let's say Bob's face is represented with this vector, 1, 3, 4, and Jenny's face is represented with the vector 3, 3, 3. Okay? So what we do is we know what Bob's face looks like, right? We have an image of Bob's face. So let's project Bob's face onto, let's take A transpose times Bob's face. So let's call Bob's face vector B and Jenny's face vector J. So A transpose times Bob's face is going to be 1, 1, 1, 2, 1, 2, 1, 1, 1 times Bob, 1, 3, 4. Let's do it out. So remember, our first entry is going to be projecting this guy, taking the dot product of these two, which basically means projecting this guy into this guy. So 1, 1, 1 times 1, 3, 4, dot is going to be 1 times 1 is 1, plus 1 times 3 is 3, so that's 4, plus 4 is 7. Okay, hopefully we can all do multiplication. So 2 plus 3 plus 8 is 13. And then 1 plus 3 plus 4 is 8. Okay, so that's Bob's. Okay, so we save those. These are our coefficients. These are our new coefficients for representing Bob's vector in the new basis, and our new basis is going to be the eigenvectors of these matrices. So this is also a change of basis matrix from our original standard basis to now representing this new vector, this Bob's vector, in terms of our old basis. In terms of our, from our old basis, which was the standard basis, to representing it in terms of these eigenvectors here. Okay, so A transpose, let's do it for Jenny, right? Whatever, 1, 1, 1, 2, 1, 2, 1, 1, 1. Okay. Jenny's is 3, 3, 3. Okay, so we get 3 plus 3 plus 3 is 9. 6 plus 3 plus 6 is 15. If I'm not mistaken, and 3 plus 3 is 9. Okay, so now we keep those stored, right? Now, some new person, now between Bob and Jenny, they have a fridge in their house. They're married, but they don't like each other. But Jenny doesn't want Bob to enter the fridge. So the facial recognition only works for Jenny. So basically, we want to identify if someone is Jenny or not. So if now someone comes in with a little bit of a change, maybe Jenny's face in this image is not going to look exactly the same, right? Because she's standing in front of the fridge. So it's capturing a different version of her face. But let's say she comes in 3, 4, 5 or something. Okay? Then we can take this, we can project it onto onto the principal components by multiplying by A transpose, and we'll get our results. So let's just do it real quick. If I multiply by A transpose, I'm doing in my head, so A transpose times 3, 4, 5 is going to be 3 plus 4 plus 5 is 12. 6 plus 4 is 10, plus 10 is 20, and then 5 plus 5 plus 5 is 15, right? All we have to do is take some sort of distance measure, and you can probably see, right? You can, this is not 1.5, this is 15, by the way. You can probably see that this is much closer to this vector than it is to this vector. And so the facial recognition system is going to say, right, okay, you are much more closer to this, so you're Jenny. And because you're Jenny, I recognize you as Jenny, you can get in the fridge and eat your snacks. Okay. That example is very crucial. You understand the example, it extends to much higher dimensions when you actually have facial data. Okay? Hopefully this makes sense. Very long video, apologies, but hopefully this clarifies the PCA process, what we're doing, what we mean when we say dimensionality reduction, what we mean when we say projecting, right? I think we covered most of it, but yes, feel free to ask any questions that you have. All right, thank you all for sticking with me.